Okay, so yesterday we were talking about arithmetic sequences, and those were sequences where we would add or subtract something every time, and it was the same something every time, remember? So if I was adding 3 the first time, I had to keep adding 3. It was a linear function. Today, we're going to be talking about geometric sequences. Okay, so slightly different. That's when we're going to be multiplying or dividing. So this is going to be in your green packet that I gave you yesterday. If you don't have any, or I'm sorry, if you don't have a green packet, there should be one in the room. This will be on page 4 where we left off. Okay. So geometric sequences. We know that this is a geometric sequence, but we need to figure out 1 times what gets me 2. Well, we multiplied 2. Again, 2 times 2 gets me 4. 4 times 2 gets me 8. So I know that I'm multiplying by 2 every time, but I need to know the next term in the sequence. So 8 times 2 would be 16. If you move on to number 2, we need to figure out what are we multiplying by every time. So 2 times what gets me 6? The answer is 3, right? 6 times 3 gets me 18. 18 times 3 gets me 54. And 54 times 3, if you have a calculator handy, is going to be 162. And over here we can just write times 3, right? So number 3, it gets a little bit different because from 16 to 8, we're getting smaller, right? So you could say that we're dividing by 2. I would rather that we say that we're multiplying by 1/2, right? 8 times 1/2 gets me 4. 4 times 1/2 gets me 2. And 2 times 1/2 would get me 1. So we're multiplying by 1/2 every time. And that's going to make things easier later once we get into our formulas that we'll be using. And then over here, last example, -1 times what gets me -4? Well, the answer is 4, right? We're just multiplying by 4 every time. So if I move all the way over here, -64 times 4 is going to get me -256. We're multiplying by 4. So that's geometric sequences in a nutshell. If we start down here, each sequence of numbers above is considered a geometric sequence. And that's because the pattern from one term to the next involves multiplying. Yesterday we were adding and subtracting. Today we're multiplying by the same amount. Okay. So if we move down here, the notes are very similar to yesterday's, but obviously now we're working with geometric sequences rather than arithmetic. So if a pattern or sequence of numbers is geometric, that sequence can be written as an exponential function, right? Yesterday we were working with linear, but today it's exponential. So to write the equation of a geometric sequence, this is our explicit formula. We had one yesterday, this one's slightly different. Still in function notation, g of n equals g of 1 times, that little dot right there is times, r to the n minus 1. Okay, r is your common, oh, this should say ratio. I'm so sorry. Get rid of that n. Should say ratio. R is your common ratio. That's what you're multiplying by. Just like yesterday, g of 1 is your first term, and n minus 1 is the term before, is your previous term, right? So to identify the common ratio r, and we want to identify also the first term for each sequence, just like yesterday, right? But now we're writing a geometric sequence as an exponential function, right? We're raising something to the power of something else, right? That's exponential. So 1, 3, 9, 27. The pattern here, well, I suppose we could start with our first term. First term right here is 1. But the pattern every time is we are multiplying by 3, right? So let's take a look again. I'm going to keep pointing back to this explicit formula. So it's really going to help us here. G of n equals g of 1, so my first term, that was 1, times r. R is my common ratio. We found that r was 3. So 3 to the n minus 1. Right? You can make that look slightly prettier. And you remember 1 times anything is just that anything. So you could even write that just like this. I would accept either answer. Okay, don't feel like you need to take it a step further. It just makes it look nicer, right? So in example 2, here you can tell we're getting smaller, but we need to figure out by what, right? So clearly we're dividing by something. So 24 divided by something gets me 12. 12 divided by something gets me 6. Well, that's going to be 1/2, right? We're cutting everything in half. My first term out here is 24. So if you look back at example 1, you'll notice that we use the dot notation, right? You could also, since it's an exponential function, normally with exponential functions we use parentheses, so I'm going to use that this time. My first term was 24, so g of 1 is 24. Then you could bring your parentheses in, right? Because I want r to the n minus 1. Well, r is 1/2 to the n minus 1. Right? So either of those notations are going to be just fine. If you use the dot notation or if you use parentheses notation, both are going to be just fine. One thing to note though, this stays like this. This is as pretty as this gets. You cannot take 24 times 1/2 to get 12 to the n minus 1. Okay? That goes against PEMDAS, so don't do it. Alrighty, we'll do one more here. So my first term, -4. From -4 to -8, -8 to -16, we're multiplying by 2 every time. So I want to take my first term, which was -4. I'm going to use parenthesis notation to take r, which is 2, to the n minus 1. Again, that is just as nice as you leave it, right? So take a second here, pause for maybe just a minute. I want you to do example 4, just to show me that you know how to do it. And then we'll come back and I'll show you the answer. Alrighty, so our first term was -64. Each time we're dividing by 4, so your common ratio should have been 1/4. And when you plug that into the explicit formula, you should get g of n equals -64 times 1/4 to the n minus 1. Okay, so that was the explicit. We're going to scoot down here. So we're going to use each formula below to find the first 4 terms. So just like we did yesterday, you'll want to keep this formula in mind. I know I'm referencing it a lot, but it is pretty important. So notice that you have your first term here, you have your common ratio here, right? First term is where we start, the ratio is what we're multiplying by. So down here, if I wanted to find the first term, I could plug 1 in for n up here. Well, 1 minus 1 is 0. If you want me to write this out here, 3 to the 0. Well, anything to the 0 power is just 1. So 4 times 1 equals 4. And we know that that's true because my first term is actually right out here, right? So I could double check that. Now, realistically, I know that we should be multiplying by 3 every time. So if I wanted to find my second term, I would plug in 2 for n, which I did here. So 2 minus 1 is just 1. So 4 times 3 to the 1. 3 to the 1 is just 3. 4 times 3 is 12. And sure enough, 4 times 3 is 12. Go through these. I want to find the third term, so I plug in 3 for n. 3 minus 1 is 2. Use PEMDAS. 3 squared is 9. 4 times 9 is 36. And 12 times 3 is 36. So we can double check that. And the last one, I want to find 4 terms. So my fourth term, I plug in 4 for n. 4 minus 1 is 3. 3 to the third is going to be 27. And 4 times 27 is going to be 108. And you can double check 36 times 3 should be 108. Okay, so that's using your explicit formula. In example 6, it looks just slightly different because now, if you look over at example 5, you'll notice that this was a exponential growth function. This, though, since the r is less than 1, this is decay. So we should actually be getting smaller every time. So g of 1, we're just going to follow just like we did in example 5. We're going to start with -1 times 1/2 to the n minus 1. Well, now n is 1. So 1 minus 1 is 0. -1 times 1/2 to the 0. Anything to the 0 power is just 1. So this ends up being -1 for my first term. Looks like a lot of math, doesn't it? Okay, we can double check that because my first term should live out here, and sure enough it does. Now I want to find my second term, so instead of n, I'm going to be plugging in 2. 2 minus 1 is 1. 1/2 to the 1. I'm going to zoom in here just a little bit. 1/2 to the 1 is just 1/2. So -1 times 1/2. Half of -1 is just -1/2. Right? And we can double check that because my common ratio should be 1/2. If I double check that half of -1 is -1/2, then we're golden. I'm going to switch colors here. I want to find my third term. -1 times 1/2 to the 3 minus 1 equals, I'm going to have you finish out example 6. You double check, you should be cutting it in half every time, but I want you to practice using the explicit formula. So maybe a minute or two, and we'll come back and check our answers here. Okay, so for your third and fourth term, you should have plugged 3 in for n and 4 in for n respectively. When you go through all of that math, you end up with -1/4 and -1/8. You can double check that because half of -1/2 is -1/4, and half of -1/4 is -1/8. Okay. Moving on to page 5. Just like yesterday, we had explicit formulas and recursive formulas. Explicit formulas is where you can just plug in the term number that you want. So if I were to just sneak back to page 4, right? If I wanted to, I could find g of 50 by just plugging in -1 times 1/2 50 minus 1, right? That would spit out a number in my calculator, right? Down here, though, with recursive formulas, if you remember from yesterday, recursive formulas mean you have to know what the term before it was, right? There's no plugging in like we can with explicit formulas. The recursive formula tells how it's related to the term before it. Okay, so likewise, the first term will always be given to you. Okay, you can't have a recursive formula without the first term. Okay, so I want you to find the next 3 terms in each of these sequences below. Just like yesterday, we're changing the notation. Explicit formulas are in function notation, meaning like g of n. Recursive formulas, remember though, this is called f sub n. That's how we say that, right? It's a subscript. That's what we use for recursive formulas. We're going to use this table here. So very similar table to yesterday, right? But if you look at our recursive formula now, instead of adding or subtracting something like we did with arithmetic sequences, we are now multiplying something, right? That 2 out front means that we're multiplying by 2 every time. So we start with our first term is 5, so that goes here. In order to find my second term, which is what I'm trying to find here, you need to know your first term. Well, lucky for us, it was given to us, 5. We know from our recursive formula that I have to multiply by 2 every time. So 2 times 5 is 10, which means my second term is 10. So in order to find my third term, I need to know what my second term was. Well, we just found it, it's 10. I know that every time I'm going to be multiplying by 2. 2 times 10 is 20. So my third term is 20. In order to find my fourth term, you need to know what your third term was. Third term was 20. We got that from over here. Every time I'm multiplying by 2, 2 times 20, it's going to be 40. So my fourth term is 40. When you write a recursive sequence, or when I ask you for this down here, write 5, 10, 20, 40, comma, dot, 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 just like yesterday. That's going to keep going on. Okay. Moving on to our G equation, example 2. So this time, looks like we are multiplying by 1/2 or dividing by 2 every time, right? So with a recursive formula, we need to start with our G sub 1. That's our first term. We have it in a few different spots here. And I'm going to take 1/2 times my previous term. That's what this means here. G sub n minus 1, that's the term before. In order to find my second term, I need to take half of the first term. So half of 4 is going to get me 2. Alrighty, to find my third term, I need G sub 3 minus 1, because I'm trying to find my third term. So I need to know my second term. We just found it. G sub 2 was 2. In order to find my third term, I need to take half of 2. Well, half of 2 is just 1. And to find my fourth term, I'm sure you guys have caught on by now. G sub 4 minus 1, that's G sub 3, which is my third term. That's what this guy means. I'm trying to find my third term. Third term was 1. In order to find my fourth term, I need to take half of my third term. Half of 1 is just 1/2. Give me the sequence written out: 4, 2, 1, and 1/2, comma, dot, dot, dot. Alrighty, I'll get you started on this next one here. Our K sequence. Looks like I didn't make a typo like I did yesterday. With our K sequence, we are multiplying by 3 every time. My starting term, my first term is -2. So in order to find my second term, I need to take 3 times -2, which is -6. I want you to follow that pattern, just like we did in the G sequence. Follow along with the K sequence. I want you to pause here. Again, minute or two, show me the math. Write down your full sequence down here. And then when we come back, I'll show you the answer. Okay, so this should be your K sequence. Multiplying by 3 every time. And then making sure to write your sequence down at the bottom with your dot, dot, dots at the end. All right, and that's notes. So your homework is going to be page 6. Just before we get into this, because I'm going to go through a few of the problems on this. Reminder, we have a unit quiz Friday, tomorrow. It's like a practice test. I have a review session that should be on the board. My review session will be in room 906, Friday, tomorrow morning at 8:05. We'll have a packet that we'll go through. You'll be able to ask questions, anything like that. If you can't make it to my review session, Mrs. Volk will have one Monday morning, and Miss Bitson will have one Tuesday morning, and we can talk more about that Friday if you'd like. And then remember, our unit test is on Tuesday. If you need any retakes done, we need to make sure that we get those taken care of. Okay, so our assignment, page 6. We're really combining geometric and arithmetic. Okay, so I'll go through the first 3 here just so we kind of get a sense of this. You need to find the next term. First of all, make sure we're reading directions. Find the next term in each sequence below, then identify if it's arithmetic, geometric, or neither. Okay, so there is a neither option. So arithmetic is when we're adding or subtracting. Geometric is when we're multiplying or dividing. Remember, if we're dividing, I would like it as a fraction. We're multiplying by a fraction. So from 6 to 9, I would check arithmetic first, because adding seems more plausible than multiplying. We're adding 3 here. From 9 to 12, we're also adding 3. 12 to 15, we're adding 3. So if I were to guess what my next term would be, 15 plus 3 is 18. And since we're adding each time, this is going to be arithmetic. Right. For those of us lost, this is page 6. For number 2, so if I check adding, here I have plus 3. Here I have plus 5. So I know right away that it can't be arithmetic, because even though we're adding something, it needs to be the same. So I'm going to go ahead and, get rid of that. So let's check geometric. What times 1 gets me 4? Well, the answer is 4, right? Well, 4 times 4 is not 9, is it? Right? 4 times 4 is 16, which is this one, but it needs to be the next term. So since I'm not adding the same thing each time, and I'm not multiplying the same thing each time, this is going to be neither. But it still wants you to figure out the pattern, right? So we kind of had something going here where we were adding 3, we added 5. Here I'm adding 7. So there's a little pattern there, right? Looks like a quadratic, because the difference here would be plus 2, plus 2. So 7 plus 2 would be plus 9. 16 plus 9 is going to be 25. So with the neithers, you might need to pick up on some other patterns here, right? It's not arithmetic, but there still is a pattern. It's quadratic. For number 3, let's check arithmetic. 1 plus what gets me 4? That's 3. 4 plus what gets me 16? Well, that's 12. Those are very much not the same thing. So it's not arithmetic. Get rid of that. What times 1 gets me 4? That's 4. 4 times 4 is 16, so we've got something there. 16 times 4 is 64. So I know it's geometric, because I'm multiplying the same thing each time. But now I need to find the next term. 64 times 4 is going to be 256. Okay. So your job will be to finish 4, 5, and 6. I'm going to go through a few of all of these, and then I'll give you time to go back and finish. So identify the next 3 terms in each sequence. The first term is given. Okay, so you're going to have to use these recursive formulas. Probably be a good idea to write that in there. This is recursive because I need to know what the previous term was. Right, so I'll go through a few of these. So if you look at 7, And it doesn't ask you to do this, but it would probably be good practice to distinguish if this is arithmetic or geometric. My first term is 12, so they brought that down here. And it says a sub n equals a sub n minus 1 minus 4. So since I'm subtracting something, this is going to be arithmetic, right? So 12 minus 4 is 8. 8 minus 4 is 4, and 4 minus 4 is 0. That's how you solve recursive formulas. I'm sorry, yeah, recursive sequences. We just move right along to number 8. It says b sub 1 is 3. That's my first term, so they brought it down for us. B sub n equals 2 times b sub n minus 1. So since I'm multiplying here, this will be geometric, right? So we're going to multiply by 2 every time. So 3 times 2 is 6. 6 times 2 is 12. And 12 times 2 is 24. And that's really all it's asking for, right? It's just telling you to find the next 3 terms. Right, I think you can handle the rest of those on your own. We did an arithmetic and a geometric one. And then the last section, it says write an explicit formula to find the nth term of each sequence given below. Okay. So I'm going to change this just slightly here. I want you to add, we're doing the explicit formula, but I also want you to add and recursive. We need practice doing both. Okay, remember explicit is function notation, and recursive was that subscript. So I will do a few examples of both to kind of get us into the swing of things here. So let's start with the explicit formula. Okay, so in 13, we need to figure out, first of all, is it arithmetic or is it geometric? If you look at 13, you can tell we're adding 3 each time. So that makes it linear. This is an arithmetic sequence. I need to write the explicit formula. Right, so this was f of n equals, if you go back, and you maybe want to just write this on the top of your page, the explicit formula for arithmetic sequences was f of n equals f of 1, my first term, plus d, that was my common difference, how much I'm adding or subtracting by, and then n minus 1 is what we're multiplying it by. That's for arithmetic. Remember, geometric was a little bit different. So for number 13, my first term, it's right here, 7, plus I'm adding 3 each time. So 3 times n minus 1. This was the part where we made it a little prettier. So 7 plus 3 times n is 3n. 3 times negative 1 is negative 3. Make this even prettier, we're going to get 3n plus 4. That's my explicit formula because it's in function notation. Recursive notation, or the recursive formula, we haven't done a lot with. However, I think it's a little bit easier to write out. I'll switch colors for you here. So this was the subscript one. So we'll start with f sub n, like that. So since recursive formulas only relate to the term before it, since this is arithmetic and we know that we're adding 3 each time, you really only need to write f sub n minus 1, my previous term, plus 3. Right? That's all we're doing to each term, because we're adding 3 each time. So this was explicit, this was recursive. And that's what it's asking for. I know I added the recursive part, but we need to get practice with it, okay? Okay, let's find a fun one here. Let's look at 16. So we did an arithmetic one. You probably see where this is going. We're going to find a geometric one, right? So let's figure out, what am I doing to make these jumps here? When there's a fraction involved, like if I go from a whole number to a fraction, probably a good idea to at least check geometric. Can't make any promises that it's actually going to be geometric, but you can tell here that every time we're cutting it in half, right? Half of -2 is -1, half of -1 is -1/2, right? So since we're multiplying, this is geometric. So our explicit formula, just scoot up here, is a little different than arithmetic. For geometric, we had, I don't know if you want to write g of n or f of n, it's up to you, equals still my first term, so g of 1, but now we are multiplying by r, that was my common ratio, to the n minus 1, right? So I will give you both of those, but it's going to be your job to figure out which is which, right? So in 16, my explicit formula, I'm going to do g of n. Remember that letter out front really doesn't matter too much. It's completely up to you. But it's going to equal my first term, which was -4, times, I'm just going to use my parenthesis notation. Like I said, you can use the dot notation if you want. My common ratio was 1/2, multiplying by 1/2 each time, to the n minus 1. The geometric sequences are nice because you don't need to make it look pretty. So that's our explicit. But now I need to find my recursive. Remember, recursive only cares about what was before it, right? So you don't need to worry about a starting term. Recursive is that g sub n equals, so this is the term that I'm looking for. I need the one before it, so g sub n minus 1. But what am I doing to it each time? Well, I'm multiplying by 1/2. And when I multiply by something, I want it out front, right? So you can write it 1/2 times g sub n minus 1. You could put the 1/2 in parentheses if you'd like. You could do the dot notation also if you wanted. I'm fine with it just reading 1/2 g sub n minus 1. Okay, let's maybe go through a couple more of these. I want to jump to 15. So 15, we need to figure out, is it arithmetic or geometric? From 14 to 10, 10 to 6, 6 to 2, looks like we're minusing 4 each time. So since I'm minusing, that's arithmetic. So we'll have to use my arithmetic explicit formula. So f of n, explicit is function notation, equals my first term is 14 plus my common difference. Well, my common difference is a -4, so I could just write -4 n minus 1. I want us to make this look pretty, so 14, -4 times n is -4n. -4 times -1 is +4. Make it even prettier. We want -4n. 14 plus 4 is +18. So that's explicit. We need recursive. So sub notation, f sub n. I only care about the term before and what I did to it, right? Well, each time I'm subtracting 4, right? So f sub n minus 1, that's my previous term. We're just subtracting 4. The recursive formula is just the term before and then what I did to it, right? Alrighty, and then let's jump to 18. This will be my last one. So figure out if it's arithmetic or geometric. 1 to 5, 5 to 25. Looks like I'm multiplying by 5 each time. It's geometric. So I need my explicit geometric function. G of n equals my first term, which is 1, times my common my common ratio, since it's geometric, was 5 to the n minus 1. Anytime you have a 1 out front, you can still make this look nicer. If you just write 5 to the n minus 1, it's implied that there's a 1 living out front. So this would be just perfect if you wrote it this way. Then I need my recursive. So g sub n. We'll start with g sub n minus 1, because that was my previous term. Well, what am I doing each time? I'm multiplying by 5. So you can just stick a 5 out front, because we're multiplying. Okay, that's really all I have for you. Your job is to get page 6 done. If you don't have page 3 done, that would be a good thing to also get done now, along with any missing homework. I want everyone to check PowerSchool to see if you have the white packet done and the pages from the yellow packet done. Okay, that is your job. I will see you all tomorrow, hopefully for our study session in the morning, but otherwise during class for our unit quiz. Bye, guys.